Let's move to a different case. This case is a uniaxial case, no stress concentration. Very strange, but I need to cover it because we're going to add a stress concentration to this case. So I want to cover this case first. Let's dive into that one. So say you have a plate, and that plate had a uniaxial stress as far field, sigma naught. And I want to know what is the stress field in polar coordinate systems. So you may ask me why I want to complicate myself. Why just not use Cartesian, given the load is only axial? The reason is when I study a letter case, which is with a hole, it's convenient to write a stress states using polar coordinate systems. So we want to first learn how to do that. And to remind you, the stress states that we're talking about here are going to look like this. So we have in the Cartesian coordinate system is going to be sigma xx, sigma xy. Sorry, sigma yy is what I meant. And then the shear is going to be sigma xy. I'm going to use a different coordinate system where this is now sigma rr. Tangential is sigma theta theta. And I'm putting the origin arbitrarily here. And then your shear is going to be a square that's distorting here. And what I want to do, I want to relate that to the far field stress, sigma naught, which is aligned with sigma xx. So you can see here that this is a problem that could have been solved very easily just using Cartesian coordinate system. Just looking at this problem, if I do a cut there, then that's clearly sigma xx equals sigma naught. So maybe I'm overcomplicating myself, but later this will be convenient to know. So I'll use the transformation from Cartesian to polar coordinate system. You can also have the reverse going from polar to Cartesian, but this is the one we're interested in. And you can see here, the majority of these are zero for our case. So in our case, you can see here that sigma x equals sigma naught because I have a plate and this is the x direction, that's sigma naught. That's the x direction. That's the y direction. I have nothing applied in the y direction. So these are zero. That means that when I plug it in, this is zero. That's zero. That's zero. So it turns out that's going to simplify to something as simple as this. And you can check it. You can check it fairly quick. You can check that this equation actually works out. I do invite you to do it so you can see it works out. So for example, if I were to look at this plate, let's look at what's going on at theta equals 0. At theta equals 0, sigma r becomes sigma naught divided by 2 times 2. I'm looking at this equation here. Sigma r with a theta of 0 means I'm looking along the x direction. And you can see that makes sense because this is equal to sigma naught. And I already told you I have a plate that's a sigma naught applied in the far field. I also expect that if I chose a theta of 90 degrees, I hope, so theta of 90 degrees means I'm looking at this angle here. So sigma r is pointing upwards now. I don't have any loads applied here. It's 0 load applied there, no load. So I expect sigma rr to give me 0. Let's see if that's true. Sigma rr equals sigma naught divided by 2. But the cosine of 180, because 2 times 90 is 180, cosine of 180 is minus 1. 1 minus 1 is 0. And I get 0. You can see that's working out really nice. I'm getting exactly what I had expected. Let's check out the next one here. So I'm going to check out, for example, sigma theta. So sigma theta is pointed always in this direction, tangential to the origin. So that's sigma theta, theta. In this case, you can see that I hope that sigma theta theta at theta equals 0 is going to give me, hopefully, at theta equals 0 gives me a value of 0. Which is, actually is not 0. It's telling me that I get a sigma naught divided by 2, which may be the solution actually for this particular case, if I'm not mistaken. At theta equals 90 degrees, I get a theta naught, which is actually what happens in this case. So the area stress function that solves this problem turns out to be this one. You guys can check that. Actually, sigma theta theta, in my opinion, should be 0. So I am making a mistake. Let me think. So at theta equals 0, sigma theta theta is equal to sigma naught divided by 2, 1 minus cosine 2 times 0. Oh, yeah, this is 1. So I get 0. That makes sense because my plate at theta equals 0, which is this one, theta equals 0, that direction has no stress. I have nothing applied there. So therefore, that makes sense that sigma theta theta is 0. And if you check theta equals 90, you should get that sigma theta theta is equal to sigma naught. So this is working. And the area stress function for this particular problem is going to give you, if you use this phi, that's going to be the solution to the biharmonic equation. And it satisfies the boundary conditions exactly. I'll let you check it at home. But everybody here knows how to apply the area stress functions. To remind you, I have it here, but in polar coordinate systems. So far, I was showing you the area stress functions in Cartesian coordinate system. But the area stress functions in polar coordinate systems look like this. And you can arrive to these expressions using polar transformations from Cartesian to polar using the polar transformations. And the biharmonic equation is going to look different. It's going to look like this. But those are the equations that need to be used. And it turns out if you apply this area stress function and you connected it to this area stress function and you actually operate on that, you will see that you get the stresses that are required to describe the stress in the plate. And you also can check that the biharmonic equation is fully satisfied.